All right, welcome. Today, we're going to unravel the powerful principles that govern chemical stability. We'll start with the classic definitions of acids and bases and build our way up to a really elegant model that solves some pretty complex puzzles in inorganic chemistry.
So let's kick things off with a classic chemical mystery. Check this out. We've got two cobalt complexes that look, pretty much the same on paper. One with fluoride is perfectly stable. The other with iodide just falls apart. And if you try to use the early acid-base theories to explain this, well, they just don't really give a good answer for why this is happening.
And the plot thickens. You take an iron 3 ion, and you look at its stability with the halides. It gets less stable as you go down the group, from fluoride to iodide. Okay, makes sense. But then you look at mercury 2, and it's the complete opposite. Stability actually increases going from fluoride to iodide. It's a total flip. So our job today is to figure out what in the world is going on here.
Okay, to get to the bottom of this, we're going to need the right tools in our toolbox. And that means we've got to take a quick trip through the history of how we think about acids and bases, because each new theory gives us a sharper way of looking at chemical reactions.
So first up, you've got Arrhenius. It's a good start, but it's kind of stuck in water. Then comes Brønsted Lowry, which is way more flexible because it's all about protons. But for what we're talking about today, the real game changer is the Lewis definition. It completely shifts the focus away from just protons and onto the real currency of these reactions, electron pairs. Defining acids as electron pair acceptors and bases as donors gives us a universal language to talk about coordinate bonds, which is exactly what's at the heart of our cobalt mystery.
All right, so with that foundation, let's get to the breakthrough idea that's going to clear all this up. Ralph Pearson's hard and soft acids and bases theory, or as everyone calls it, HSAB.
And here's the core idea, right from Ralph Pearson himself. I mean, how simple is that? It's this super intuitive like-likes-like rule, and it just beautifully organizes tons and tons of experimental data into one simple framework.
And this is absolutely crucial to get. These two like-like interactions are driven by totally different types of bonding. When you have a hard-hard interaction, think of it as pure electrostatic attraction. It's like two tiny, powerful magnets snapping together, mostly an ionic thing. But with soft interactions, it's a whole different ballgame. This is all about covalent bonding. You've got these big, squishy electron clouds that can easily overlap and share electrons.
Okay, so this hard and soft language is great and all, but what does it actually mean chemically? Let's break down the properties that define them. So, hard acids. Think small, think compact, and usually they've got a high positive charge. When you pack all that positive charge into a tiny space, you get what we call a high charge density. Imagine them as these tiny, dense little balls of positive charge. Their electrons are held super tight, so they're not easily distorted. And you guessed it, soft acids are pretty much the exact opposite. They tend to be much bigger, with a lower positive charge, which means a low charge density. And here's the key. Their outer electrons are kind of floppy and spread out. This means their electron clouds are easily squished and distorted. We say they're highly polarizable. And that is what makes them so good at forming those covalent bonds.
And this whole logic, it applies perfectly to bases too. Your hard bases, like fluoride, are small, super electronegative, and they guard their electron pairs like a dragon guarding treasure. They are not sharing easily. On the other hand, soft bases, like iodide, are big with a diffuse, polarizable electron cloud. Their electrons are way out there, just ready and willing to be shared in a nice covalent bond.
But chemistry is never just black and white, right? Of course, there's a gray area. We call these borderline cases. They're kind of in the middle, and they can play for either team, hard or soft, depending on the situation they're in.
Okay, so now we've got this whole classification system down. We have the tools. Let's go back and finally crack those puzzles we started with. So let's take a look at the silver halides. Ag+, the silver ion, is a classic soft acid. Iodide, I-, is a classic soft base. They're a perfect match, soft-soft. So that Ag-I2- complex forms super easily. But fluoride, F-, that's a hard base. So you try to mix a soft acid with a hard base, and nope, mismatch. The Ag-F2- complex just doesn't exist. It's a beautiful illustration of the principle. And now for the big one, the mystery we started with. Cobalt-3, Co3+, is small with a high positive charge. That makes it a textbook hard acid. And fluoride, F-, it's a perfect partner, a hard base.
Hard, they form a super stable complex. That's why CoF63- is so stable. But then you bring in iodide, I-. That's a soft base. You're trying to pair a hard acid with a soft base. It's a terrible match. That's why CoI63- is so unstable it basically doesn't exist. And hey, this also perfectly explains that iron trend we saw. F3+ is also a hard acid, so of course it loves the hardest base, fluoride, the most. The mystery is totally solved.
Okay, this is where it gets really cool. This like-likes-like idea goes even deeper into something called symbiosis. The basic idea is that ligands of one type, say a bunch of hard ligands, can actually make the central atom harder, which then makes it attract even more hard ligands. It's like they reinforce each other.
A perfect example is boron trifluoride, or BF3. You've got a boron atom surrounded by 3 super hard fluoride ligands. Those fluorides are pulling so much electron density away that they basically harden up the boron atom. So when it's looking for a fourth partner, who do you think it's going to prefer? Another hard base like ammonia. Hard attracts more hard. That's symbiosis.
Now, HSAB is an amazing tool. It's incredibly powerful. But, and this is a big but, it's a model. It's a guideline, not an unbreakable law of the universe. And to really understand this stuff at a deeper level, we have to look at where it breaks down.
So check out this reaction. At first glance, it looks pretty simple, but it's actually going to throw a wrench right into the rules we just learned.
All right, let's put on our HSAB goggles and analyze this. Okay, the proton, H+, that comes from HF. That is the hardest acid there is, period. And in this reaction, it's leaving its hard partner, fluoride, to go and bond with sulfite, which is a soft or at best a borderline base. So wait a minute, a hard acid is ditching a hard base to form a stable bond with a soft base? That's the exact opposite of what the HSAB principle predicts. Our simple rule says this shouldn't happen, but it does.
So this begs the question, what's really going on here? What's the deeper theory that explains why the rule works most of the time but fails here? And that's where we have to level up to something more sophisticated, like frontier molecular orbital theory. It doesn't just talk about hard or soft, it looks at the actual orbitals involved. The highest energy orbital with electrons in the base, the HOMO, and the lowest energy empty orbital in the acid, the LUMO. If the energy and the shape of those two orbitals match up really well, you can form an incredibly strong bond even if HSAB would have predicted a mismatch. It just goes to show, in chemistry, there's always another layer to uncover.